Okay, so here's the next bit on area rule. What's called a Coke bottle fuselage or Whitcomb rule. Okay, good aircraft to look for examples of this are, so for wing fences, you're looking at early Sukhois, I think the Sukhoi, I want to say the Su-22, right, also Tupolev, I think it's the Tu-22 blinder, I think they have wing fences, I can't remember off the top of my head, right. Delta wings, look at the Vulcan. King of all deltas really is the Mirage, yeah, the French Mirage, the Mirage, either the Mirage 3 or the Mirage 2000, okay, they're your deltas. What else, things to look for, anhedral, we're looking at Harriers, here's the best example of an anhedral wing. Sweepback, lots of sweepback, F-86 Sabre. There's a good example of a sweepback wing. An area rule, okay, the best one I can find actually if you look down from the plan view is the F5 Tiger. So there's some examples of those. Right, so what is area rule? We mentioned before the shockwaves don't like getting caught on a bump, okay? If you have an aircraft where if you're looking down on it, yeah, and there's a famous story for area rule, there's the F102, I might get this a bit wrong, there's the F102 Delta Dart and the F106 Delta Dagger. I might have got them the wrong way around. Anyway, F102, F106. The early F102s, which were very early American Delta fighters, a bit like a Mirage, they look like a Mirage, okay, just a basically triangle with a couple of wings on. If you imagine if I show you my model Typhoon there, one of those without the canards on, okay, without those canards, just a standard Delta configuration. Single engine, okay, and the fuselage looked like this. And basically, it was just a big pointy thing like that, yeah, and then they had the Delta wings on like that, yeah, and Delta wings, no problem with separated flow, messing about with the tail. They had little air intakes at the front there, yeah, and then it had a single engine, and they threw that at the sky and they says, oh, that should do Mach 2, or I think they were heading for about Mach 1.6 with the F102. Design speed, wind tunnel test, and Mach 1.6 is going to go fine. What they found was, at the thickest point in the wing where these shock waves were happening, okay, the thickest point of the wing was also the thickest point of the fuselage, because you have to make it like a slightly bulge here, yeah, it has to be that big, because inside that's where the engine is, yeah, so this bit's all engine, okay, so instead of, and the engine actually probably only started, yeah, the actual engine bit was probably only this bit here, but they'd widened it up so that tube, that's where the engine fit in. What they worked out was that when the air was trying to go, if you take a cross-sectional slice through that, okay, you'll find you've got the fuselage and the thickest part of the wing, yeah. So what they worked out is, if they can make where the thickest part of the wing is, if they can make the fuselage thinner, the shock wave would would move back faster. The shock wave wouldn't get stuck on the bump, because the shock wave's trying to push this through the air. The shock wave says, oh, you know. So what you do is, if you make the fuselage thinner at that point, right, like a Coke bottle, you've reduced the cross-sectional area at that point, yeah. So where the wings get thick, if you take a slice through here, take a slice through there, you'll see that slice through there would be the fuselage and a little bit of wing, yeah, okay, and the slice through here would be the fuselage getting slightly thinner, and the wing would be thinner as well, because the wing gets thinner towards the trailing edge, okay, so that was the idea behind it, alright, so where the wing is thickest, that's where the wing is thickest in the middle, and that's where the wing's also the most cambered, if you can make the fuselage thin at that point. And that's what they did with the later models of the F102 and the F106. And what they did was, they just made that bit, the fuselage, a little bit thinner. Okay? So, and all that is inside the fuselage is just a duct, so that the air can go. You've got the cockpit, the pilot sitting there, you've got a radar. Behind this you've just got fuel, and a hole in it so that the air intake can suck in air and feed it to the engine. So they could make that part of the fuselage thin, okay, that part of the fuselage structure thin, and it meant that the shockwave didn't get caught on the cross-section area of the fuselage and the wing, trying to push it all through the air at the same point. It made the shockwave form further back and also made the shockwave move further back with more ease without getting stuck on the wing, causing what we call wave drag. If we have a large shockwave stuck on a bump, right, what we have is the energy of the air having to go in that shockwave and out the back of the shockwave, and the energy of the air colliding and compressing in the shockwave can be measured and transferred into heat. That heat is transferred into the airframe, but also that energy required to generate that heat is energy that the engine is having to produce to push it through the air. That's how mathematicians work it out. Even if you forget the heat bit, okay? If you want to compress air in a shockwave, you're going to have to get energy from somewhere, and that energy comes from the energy that you're pushing the aircraft through the air with. Yeah, forget that bit for now, okay? That's getting into a bit more advanced than you need to be. Right, make it thin in the middle, like a Coke bottle, like a wasted section like a Coke bottle. And a good example of that is the F105. That has two little intakes there. It has two little engines at the back, and that has standard wings. It's got a wing like it's got a little wing like that. Yeah, and the F105 has a very wasted section, and then like a fat bum with two engines, and it has some tail ones on the back there. Sorry, not the F105, the F5. Sorry, I'm just getting confused there. Okay. Why don't you see it on more modern aircraft? You do, but it's a lot more subtle. Okay. If you look very closely, I don't know if the light's actually, it's getting darker here. So if you look very closely at the Typhoon, you can see that. Just hang on that way. Probably see that where the engines are is thicker than this part here is thinner, right? And the thickest part of the wings is actually, when you look up close to the wings, is the front leading edge of the wing. Where I'm running my finger along there, that's the thickest part of a Typhoon wing, and where it is thickest, that is thinned down there. Yeah. Now you don't have to have the front. You don't have to have the Coke bottle shape. You don't have to have the front thick, the middle thin, and the back end thick again. If you can make this part thinner and the front thinner, that's great. Okay, that's even better. Okay, so you can see that bit there is where it's area ruled slightly. Okay, it shows on the bottom as well, where you just see that bit where the fuselage thins in. So most modern aircraft go for some form of area ruling, right? Airliners do it as well, because airliners are trying to fly at Mach 0.9 close to the sound barrier. Right, sweep back. Okay, so this is the thing I wanted to draw for you. Okay, the sweep back. What I'm going to do, I'm just pop the light on, because I think we've got enough light on here. It's gone the clouds have come in. I normally use the skylight in the back of the room. Right, that's probably better. Right. Okay, dead easy. You've got a straight wing. Okay, and we're going to rotate that wing and we're going to sweep it back. So we're just going to sweep that wing back like that. It's the same wing. It's got from the side. If we now cut a cross section through there, okay, and we go and we draw the cross section, we will see that it looks like this. And it's an aerofoil, and it's that shape, and it is whatever, yeah, 10 centimeters thick. I don't know. I don't care how right. Yeah, we'll see it's 10. It's 10 centimeters thick. Okay. Now, if we cut a slice through the same wing, yeah, and instead of going that way, we go this way. Okay. And we draw that slice side on. That line there is longer than that line. Okay, so that slice is going to be like that. It's not perfect, it's meant to be an impression of an aerofoil, okay. Bit better, right. So it's longer, okay, but inside this bit here is still 10 centimeters thick. I haven't made the wing any thicker. But from the perspective of the oncoming airflow, remember, shockwaves don't like bumps. So the air here comes along, it has to go up a steep bank and a bump and a big curve. Yeah? The airflow going over this wing, on the swept back wing, is going up from the perspective of the airflow, a more gradual curve. Right? The change in camber is more gradual. Here's a key sentence for you. The change in camber is more gradual. So then there's less of a bump for the shockwave to stick on. Yes? If we then turn that wing and make it a swept back wing, you'll see that that was our original cross section, and now our cross section here is from, this is the direction the air is going to come in, this way. Yeah? So when air travels over a swept back wing, it has a chordwise and a spanwise component. Yes? And the chordwise and spanwise component, basically this is the best way to forget chordwise and spanwise components. The best way of seeing it is from the perspective of the airflow. Yeah, if you cut two cross sections through the wing and draw me that, you'll see that that is a less steep curve. Okay? Which means you will get a smaller, right, shock wave, because there's less camber to produce that acceleration, and that shock wave will move backwards more easily. Right, so the shock wave appearing there will have less of a bump to go over, it'll be smaller, whereas here you'll start off with a big shock wave at the front and it will move backwards more slowly. Okay, there's more bump for the shock wave to overcome. Right, so a smaller and weaker shock wave on a swept back wing will produce less wave drag, okay, and it will also, that nose up nose down effect that you get will be lessened because you're not destroying as much lift when the shock wave forms. So it will not alter the balance of the aircraft as much because the shock wave is smaller and covering less area. Got that? Right, there are disadvantages of swept back wings, which we'll come to in a minute. And by the way, for a wing to be swept back, technically, this kind of thing here, where we've got the cross section, if your wing wasn't a true swept back wing, like say an F-16 or something like that, where the tail section, so what's bang up to date, your F-22. Your F-22 wing is that sort of shape, isn't it? If you take that out, that's your F-22 wing. But you can see with your F-22 wing, that line there and that green line there, the green line's still longer than the red line. Okay, it's about the sweep of the leading edge of the wing. That's what defines really a swept back wing. A true swept back wing has both edges swept back, but any sort of sweep back on the leading edge of the wing gives you a swept back wing effect. Right. The reason a lot of fighter planes, you'll see more modern fighter planes have, instead of having a wing like that, like your F-86 Sabre wing, the reason they have this bit filled in is because it's more wing area, so it makes them better dogfighters. Yeah, we've done that already when we did turning forces in a turn. If you've got more wing area, it reduces the wing loading of the wing, which means you can have a stronger wing. Or you can spread the forces of an aircraft pulling lots of G's and the extra lift required in that turn in a dogfight. You can spread it over a bigger area, which means the wing doesn't have to be as strong and it can be lighter. More wing area means less wing loading, which means lighter wings. Okay. Sort of. Obviously, more wing area means you've got to make more wing, which makes it heavier. But we've got no point with Transonics there. Where was I? Right. So sweep back. So that's why sweep back. So that's how sweep back affects stability in the that's the speed part of sweep back. Okay. It makes the shock wave smaller and makes it form a bit further back. Now, the other part of sweep back is as the aircraft side slips, okay, as we saw with dihedral, right? So when the aircraft side slips towards you, there you go, there's an aircraft with straight wings, okay, it's now side slipping towards you, and as you see, I'll just go a bit closer in, this aircraft has dihedral, so the downgoing wing, so we've turned and we're side slipping, so the camera is now, let's get this lined up better, the camera is now the oncoming airflow, the oncoming airflow with a side slip sees the aircraft from this perspective, and it can see more of this bottom surface of the wing, of the downgoing wing, so it acts on it because this downgoing wing has an increased effective angle of attack, which will push the aircraft back into level flight. Okay, so from the perspective of that was, the aircraft comes along, it side slips, yeah, the air is now coming from this direction, it pushes back on the dihedral and rights it. Sweep back has the same effect. Okay, there's a swept back wing. Okay, when the aircraft's flying towards you, okay, you can see equally both sides of the wing, both. So now, instead of a higher effective angle of attack, it has a higher effective aspect ratio. If our Typhoon side slips, okay, the oncoming airflow will see it from this position. So obviously you can see all of the front section of this wing and very little or none of the front section of this wing. Right? That means as it side slips, this wing, right, is hitting the airflow at an increased angle, right, at a more head-on angle, which means that the downgoing wing in a side slip on a delta wing or a swept back wing will increase its lift. Okay, so as the aircraft side slips, because it's swept back, it will increase the lift on the downgoing wing because of side slip, and that will right the aircraft, it will give it some stability. So delta wings and swept back wings can make the aircraft more laterally stable. Okay, as the side slip, yeah, and it's about how much of the wing, right, it's about how much of the wing, I'll just get lined up with the camera a bit better, it's about how much of the wing, the side slipping air, the new relative airflow can see more of this wing than it can of this wing. So it acts upon it, and it acts upon it creating lift, and it pushes it back into level flight. Now, so that's how sweep back can make the aircraft more laterally stable. It also happens, swept back wings, if it yaws, if the aircraft yaws left and right, the same sort of thing happens. So if the aircraft yaws to the right, if it's disturbed to the right, you'll find out that this wing, as well as creating more lift, this wing will create more drag. Okay, so as this wing is forced through the air, the angle changes, so it's more head on to the air, it will create more drag, which will push it back into line. Okay, if you have a straight wing aircraft, so that gives the aircraft, sweep back gives the aircraft more stability in roll and yaw, or in lateral and longitude, in lateral and in the directional axis. Now the straight wing, if you go that way or that way, you can still see, you know, as you move the aircraft along there, you can still see equal amounts of the wing as it yaws. So that doesn't have that effect. Okay, but a swept back wing will. Right. So that's how sweep back. Sweep back does loads of things for you. Makes you smaller, weaker shock wave. Okay, it reduces the form drag, because instead of hitting the air straight on it, the air is going to hit the leading edge of the wing at an angle and slip off it